In this lecture, we want to establish the main differentiators between linear motion and rotational motion, but also discuss the similarities between the two. Because in a lot of ways, there is not much difference between what we did in Chapter 2 and what we're going to do in Chapter 9. It's just a different way of thinking about things. And it all boils down to something that we've known for a very long time since we first did trigonometry. So let's talk first about what rotational motion is and what the basic assumptions that we're going to use in circular motion are. First of all, we know that if we are in circular motion, one of the most important aspects of being in a circle is that in a circular motion, you can define a radius. And what is the basic definition of a radius? It is the points equidistant from the center of the circle. And at any point that you are along the circle, even though I drew the circle very poorly, are all at the same radius. So one of the most important things to recognize then is that the radius is going to be a constant. And we're going to use this over and over again in our ideas here. Now, if we want to look at something going in a circle, then what is going to be happening in reality is that basically if something is in a circle, it might be at point 1 and then at a later time be at point 2, point 3, point 4, at all sorts of points along the circle where the radius is going to remain constant throughout. But we're talking about motion, not just staying still on a circle. So we have to define some concepts such as velocity and acceleration, just like we did in Chapter 2, but how they relate to you being, well, on the circle. So the most important concept that we had back in Chapter 2, we recall, was how velocity related to displacement or distance. Namely, if we had a function for distance, then we were able to ascertain the velocity by taking its first derivative, and once we had that, then we can take the second derivative, and so on and so forth. Well, what is the way that we can talk about distance on a circle? Well, if we look at any points along the circle, this is how we would define the distance here, denoted by s. And we remember from high school trigonometry that there was a very, very useful equation about circles which defined s to be what is called arc length. And we remember that arc length, s, is equal to the angle that you draw out multiplied by the radius of the circle. Well, if you're on the circle, we know that you're drawing out an arc length, but if you were the thing on the circle itself and you didn't realize you were on a circle, you would say that this is just a linear distance. Namely, this is an equation which can link rotational motion to linear motion. So from here on in, instead of calling it s for arc length, we're just going to call it x, because we recognize that it is just a linear distance, and so we're going to say that x is equal to theta r. And this is going to be our first and most important equation in this entire chapter. And so sticking with our numbering system from the previous chapters, this is going to be equation 20. We're also going to give this another name, which is the link equation, which will become very important when we're trying to draw the corollary between linear motion or one-dimensional motion and circular motion. Okay, so let's go over to another place. And so if we remember how we had highlighted our equations from Chapter 2 here, let's see if we can come up with the first equation that will be useful for rotational velocity. We know from Chapter 2 that equation 1 tells us that v is equal to dx dt. But equation 20 tells us that x is equal to theta times r. So if we plug that in, then what we see is that velocity is equal to the time derivative of x, which we've now called theta times r for something moving in a circle, which by the product rule is going to be d theta dt times r plus r d theta dt. But we had already said something about r, namely that the radius is constant. Oops, and I apologize, this one should have actually been a dr dt, and this should have been a theta here. But the point nonetheless is the same, because we recognize that since the radius is constant, this whole first term vanishes, and so we're left just with r d theta dt. What does d theta dt represent? It represents that as you're moving on the circle, how the angle changes with time. Well, let's give that a name. Let's define omega to be d theta dt, and we'll call this the angular velocity. And if we do so, then what we see is that v has a very nice relationship between linear motion and angular motion, namely that v is equal to r omega, where omega is d theta dt. And we now have our first angular analog that we'll call equation 21 that shows how angular velocity, omega, relates to the angle function, but also how we have another link equation which shows how velocity relates to the angular velocity, omega. And so this is going to become of the utmost importance. If we follow the same line of thinking, but now start from equation 2, where acceleration is dv dt, we can now plug in the link equation from above for velocity, which tells us that acceleration is the time derivative of r omega, which by the same rationale as above is dr dt times omega plus r d omega dt, which again, since the radius is constant, just leaves us with r d omega dt. And if we let alpha become d omega dt, namely we have just defined how much your angular velocity is changing around the circle, so this is now our angular acceleration. Then we see another link equation has manifested between the linear quantity a and the angular quantity alpha, where we have now defined the angular quantity alpha as being d omega dt, and we'll call that equation 22. And we now have our next link equation as well that relates the angular quantity to the linear quantity. If we do this again, but now to build our analogs of equations 3, 4, and 5, let's start from equation 3. Equation 3 says that v final is equal to v initial plus at. But now, in this equation, let's use the link equations for v final, v initial, and acceleration. Obviously, we don't need to plug anything in for time, because whether you're going around in a circle or in a straight line, time is always the same. What this then means is that v final becomes r omega final is equal to v initial, which becomes r omega initial, plus a, which is r alpha times t. Well, this is very interesting because we can factor out an r, which is in common in each term, and we have r omega final is equal to r times omega initial plus alpha t, and divide out the r, and we get left with omega final is omega initial plus alpha t. And we see that this is a rotational analog which looks just like equation 3, but only where each of the linear quantities are replaced by angular quantities. And so we call this equation 23. If we continue to play this game, we're not going to be surprised at the results. Namely, if we then start with equation 4, then what we will get is x final is x initial plus v initial t plus 1/2 at squared. And once again, use the link equations for x initial, x final, v initial, and a. In doing so, then this equation becomes, just like we did above, r theta final is equal to r theta initial plus r omega initial t plus 1/2 alpha r t squared. We can once again factor out the r, and we get r theta final is r times theta initial plus omega initial t plus 1/2 alpha t squared, and divide out the r, and we get a rotational analog which looks just like equation 4, except all of the linear quantities have been replaced by angular quantities, and we'll call that equation 24. The derivation of equation 25, which would be the angular analog of equation 5, is left as a homework assignment. So let's go over to our summary. If we want to draw the complete story in summary, we've seen that the analog of equation 1, the rotational equivalent of velocity around a circle, we define as omega, which is d theta dt, and we call that equation 21. Alpha, which is the angular acceleration, is d omega dt, and we call that equation 22. Equation 23 was our analog of equation 3, which said that omega final is equal to omega initial plus 1/2, plus alpha t, and that was equation 23. Theta final was equal to theta initial plus omega initial t plus 1/2 alpha t squared, which was equation 24. And omega final squared is equal to omega initial squared plus 2a delta theta. So we see that in order to get this one-to-one relationship between the linear motion and the rotational motion, that linear motion relied on us knowing information about the linear distance, x, whether it's a function or something about it, whereas rotational motion requires us to know something about the angle. Then we were able to say that if we know that, then equation 1 and 2, and therefore 21 and 22, knowing functions of theta is the same as knowing functions for x in linear motion. Knowing functions for omega is the same as knowing functions for velocity in linear motion. Then, just like how we had in linear motion, for when we have constant acceleration, equations 3, 4, and 5 hold true, whereas equations 23, 24, and 25 hold true for constant angular acceleration, alpha. So these were our constant A. These are our constant alpha, which, if you remember the link equation, constant A, since radius is constant, would also imply constant alpha. What are those link equations? Well, again, we started this by saying the first link equation was from trigonometry, that a linear distance is equal to theta r, which we then took some derivatives of these and said that v was equal to omega r, and we took another derivative to say that a was equal to alpha r. With these three link equations, we see that rotational motion is nothing more than linear motion in disguise. So if we take out all of our bag of tricks of problem-solving techniques from Chapter 2, we'll be able to directly apply them to Chapter 9 without too much worry. There is one more piece of this puzzle which is missing, and that will come in a later lecture. The next lecture will feature that missing piece of the puzzle, as well as talk about how to approach some basic problems. Until then, never stop thinking.